Yes, myself, Dr. R. Kavitha, Assistant Professor of Chemistry, Sri Sharda College for Women. In this video, I am going to discuss the topic polarography. This topic in Module 4 of Physical Chemistry 2 in 6th semester of 3rd BSc Chemistry. So in this lecture, we will study about the principle of polarographic method, instrumentation and applications. Yes, let us see one by one. Coming to that, introduction to polarography. This polarography is a voltammetric method. This voltammetric technique, which is used to study the behavior of electroactive species at the surface of dropping mercury electrode. It is abbreviated as DME. What is electroactive species? The electroactive species is nothing but it is a chemical species which undergo oxidation or reductions. In terms of electrochemistry, oxidation means loss of electron and reduction means gain of electron. This method involves the measurement of current as a function of applied potential. This method was invented by J. Jaworski in the year 1922. Okay. Coming to that, the principle of polarography. The principle of polarography is based on the electrochemical oxidation and reductions. In this method, gradually we are increasing the negative potential which is applied between the two electrodes. The two electrodes are polarizable electrode and non-polarizable electrodes. The polarizable electrode, otherwise it is called as indicator electrode, and non-polarizable electrode is otherwise called as reference electrode. Here in this method, the dropping mercury electrode is used as a polarizable electrode and the saturated calomel electrode is used as a non-polarizable electrode or a reference electrode. And this method involves the measurement of current resulting from the electrolysis of a solution at a dropping mercury electrode. So here the main principle is the electrolysis of a solutions. Okay. So now by this, what is the process of electrolysis? The current is flowing between the two electrodes, which is recorded as a current voltage curve. It is called as polarogram. It is in the shape of sigmoid shape, that is S shape. And this technique is called as polarography and the instrument is named as polarograph. Using this method, one can perform qualitative and quantitative analysis. And the phenomenon occur in that principle of the polarography is it involves the formation of a diffusion layer around the electrode. Diffusion layer is nothing but which is the formation of a Helmholtz electrical double layer which influencing the measured current. Okay, so let us see a typical polarogram which is usually obtained for every measurements. Yes, so this is the type of polarogram which is usually obtained for any of the measurements. One can find that there are three different currents can be measured from the polarogram. The first one is residual current, the next one is diffusion current, and the third one is limiting current. In addition to these three currents, you may get one more information that is called half-wave potential. So here the first, in the polarogram, you look at the graph. So here the A to B is called as residual current and B to C is called as a diffusion current and C to D is called as limiting current. So initially when the potential is applied at DME which is equal to the reduction potential of the metal which is present in the solution. Then once the potential is equal, then the metal ion it starts to reduce at the surface of a mercury, so that the current is starts increasing from B to C is due to the cathodic reactions, which is known as a diffusion current. Okay, let us see that all the three currents in detail. The first one is residual current. It is otherwise called as charging current or condenser current. The current that flows in the absence of the depolarizer due to the supporting electrolyte is called as residual current. And this residual current is the sum of a relatively larger condenser current and very small Faraday current. The condenser current is called IC and the Faraday current is IF. So here the residual current IR is equal to IC plus IF. Okay, IC means condenser current. It is due to the formation of Helmholtz double layer at the mercury surface. And IF is Faraday current. It is due to the presence of the impurities which is present in the solutions. Once if you have the greater the residual current, lesser will be the sensitivity of the polarographic method, because the residual current is mainly due to this, what is that, the formation of a double layer and the presence of impurities, isn't it? So in all the measurements, as minimum as possible, the residual current should be minimized in all the measurements. Okay, then how to minimize this current? So this current can be minimized by taking the reading at the end of mercury drop just to fall, isn't it? When it just to fall, where the rate of change of surface area is minimum, so at which the residual current is also minimum. Okay, so now coming to that, the next current is called diffusion current. So this diffusion current is produced due to the oxidation and reduction of the electroactive species. As in the polarigram, we see that it is in the curve BC. It is in the curve, it is BC. That is, it is the difference between the residual current AB and limiting current CD, isn't it? So that is ID is equal to IL minus IR. As we already discussed that when the applied potential is equal to the reduction potential of the metal, then the metal start to reduce and it produces a Faraday current, isn't it? And actually here it is that the main reason for the diffusion current is actually the diffusion of electroreducible ions from the bulk of the sample to the surface of a mercury droplet due to the concentration gradient. So here the bulk we have a more number of ions and in the surface we have a less number of ions. So there automatically what is it, produce a concentration gradient. So the concentration gradient act as a driving force and it moves that molecules from the bulk to the surface of the mercury droplet. So that is the current produced from the actual diffusion of ions from bulk to the surface is called as a diffusion current. And this diffusion current is used for the determination of concentration of the substance. That is, when we increase the concentration of the substance or decrease the concentration of the substance, that will alter the diffusion current. So one can get the concentration of the substance from the diffusion current value. The next current is limiting current. As you look at this diagram, so first one is residual current, the next one is diffusion current. So actually the diffusion current, it starts increasing and it follows a straight line. Okay, and beyond a certain potential, the current reaches a steady state. This value is called as a limiting current. Actually here the current is limited by the rate of transport of the reducible cation to the electrode. Okay, so and that is the rate of the reduction process and the transport of ions to the electrode is same. That is, the rate of the process is become equal, then the current is limited. That is, once all the ions get reduced, that is, the current is almost to become constant. So the maximum current that flows includes the contribution of residual current, diffusion current, and another one term is called IM. We know IR is residual current, ID means diffusion current, and what is IM? So this IM is nothing but migration current. Okay, it also influences the limiting current. So it must be included in the limiting current. Okay, so that is here. At the point of limiting current, the rate of diffusion of ion is equal to the rate of reduction of ions. That is, the state of electrode is said to be concentration polarized. Your electrode is concentration polarized. Okay. So now we will see what is IM. That is migration current. So the migration from the term. So that is the migration of cations from the bulk of the solutions towards the cathode due to the diffusive forces irrespective of the concentration gradient, whatever it is applied to the solutions. Then mainly this diffusive force is proportional to the electrode potential gradient. Okay, so then how to eliminate this migration current? Okay, so it is eliminated by adding 50 to 100 fold excess of inert supporting electrolyte. So usually for the electrolysis reaction in the polarography, we used to have a electrolyte. In addition to that electrolyte, we are just using a inert supporting electrolyte. So either it is used as either sodium chloride or a potassium chloride. It is inert supporting electrolyte. That is, both the sodium and potassium will not discharge at the cathode. That is, it do not interfere the analysis, but it minimizes the migration current. Okay, then the next, the important information from the polarigram is half-wave potential. Here the half-wave potential is the potential at which the concentration of oxidized and reduced forms at the electrode surface is equal. That is 50% of oxidized and 50% of reduced forms are present. Okay, as have you clear about this? So this point is called half-wave potential. This point, that is the center of the sigmoid curve. The center of the sigmoid curve is called half-wave potential, at which the 50% of oxidizable species and 50% of reduced form is present. Okay, so here this half-wave potential is characteristics of every element. It may not same for all the elements. It is entirely based on the particular element. So from that half-wave potential, one can identify the nature of the element present in the solution. Okay. So now here we have discussed about the different currents which is appeared in the polarigram. Okay, so then how to measure this current? Okay, so this current is measured in the form of a equation. Okay, so that equation is called as a Elkovic equation. So it is the relation which is used in polarography relating the diffusion current ID and the concentration of the substance which is to be reduced or oxidized at the dropping mercury electrode. So here the ID, the term ID is diffusion current, which is measured in a microamperes, and the first one is 607. It is simply a constant. This constant is a various constant of the various numerical factors including the Faradic current and density of mercury, etc. And N is the number of electrons involved in the electrode reactions, and capital D is the diffusion coefficient of the solvent. Another M is the viscosity of the, that is the weight of the mercury. Sorry, it is the weight of the mercury which is flowing at the capillary, and T is drop time in seconds. Okay, and C is concentration of the reducible species. Okay, so here the concentration is directly proportional to ID. So once the concentration is increases, the diffusion current is also increases. Okay, so here what is that, the number of electrons involved in the reaction will influence the diffusion current, as well as what is that, the mass, the weight of the mercury, as well as the drop time of the mercury and the diffusion coefficients, all will influence the measured diffusion current. In addition to this N, D, M, T and concentration, we have some more factors which will affect the measured diffusion current. Then what are the factors which influence the Ilkovic equation? As we discussed in the equation, M and T, that is mass and the drop time, isn't it? So it will change the dimension of the capillary and applied pressure of mercury reservoir to form a drop. So in addition to that M and T, that the capillary dimension, the dimension of the capillary, it also indirectly influence and applied pressure of mercury, because this applied pressure only decides the drop size. And the next one is the height of mercury column. Okay, so based on the mercury column height, the drop may get varied. Another important thing is applied voltage. So here there is in the previous equation, you look at this, there is no term applied potential, isn't it? But in the graph we have what is it, the current versus applied potential. But here there is no term regarding the applied potential. But this applied potential influence the Ilkovic equation. In what way means this applied voltage produce some changes occurring in the surface tension of a drop at the tip of the electrode. So it is responsible for the surface tension of the drop. So if we change the applied potential, the surface tension of the drop is also get varied. Okay, and the last one is the variation in temperature and viscosity. As in the equation, Ilkovic equation, there is no term temperature and there is no term regarding viscosity. But this temperature and viscosity will indirectly influence the Ilkovic equation, because it what is that, disturb the diffusion coefficient most significantly. Once the temperature and viscosity of the solution has changed, the diffusion coefficient is also changed. But this diffusion coefficient is directly proportional to the ID. So it is indirectly influencing the measured diffusion current. Okay, so up to this we have discussed about now the principle of polarography and the typical polarigram, and what are the different currents in the polarography, and in what way the current is measured in the form of Ilkovic equations. Okay, so now we are just coming to that instrumentation part of the polarography. Okay, so here this polarography is set up. It consists of a 3 electrode system. One is working electrode, that is a dropping mercury electrode. Another one is a reference electrode. So it is usually, the reference electrode is standard calomel electrode, like, and sometimes even platinum electrode is also used. And the next one is auxiliary electrode, which means counter electrode, So here this counter electrode, that is auxiliary electrode, it functions as a cathode if the working electrode is anode. If the working electrode is cathode, this auxiliary electrode will act as anode. So it's just like vice versa. So, and always it often has a large surface area. It often has a large surface area and it provides a circuit over the measurement. Okay, and here we used to have a potentiostat. It is used to control the applied potential to the working electrode. Okay, let us see that instrumentation in detail. First, we look at that the construction of this instrumentation. Okay, so here the assembly consists of a mercury reservoir at the top, and it consists of a fine capillary, that is glass capillary. It with the size range from 20 to 50 micron, and the centimeter, the capillary length is 10 to 15 centimeter. And this capillary is connected to the mercury reservoir by rubber tubing. Okay, and a small glass electrolysis cell. This is a glass electrolysis cell in which the unknown solution is placed. And the height of the mercury reservoir is adjusted so that the drop time is 1 to 5 seconds. That is, for a second, the one drop will take minimum 1 to 5 seconds. And the dropping mercury electrode is used as a polarizable electrode, and that is, it acts as both anode as well as a cathode. And the pool of mercury is act as a counter electrode, and that is, it is counter electrode means that is anode if DME is cathode, or cathode if DME is anode. And here the counter electrode is otherwise called as a non-polarizable electrode. So here to the analyte solution, as we already discussed, that electrolyte, the supporting inert supporting electrolyte, that is potassium chloride, is added, that is 50 to 100 times of the sample concentration, that is excess of the 100 folds of excess of the supporting electrolyte is added to minimize the migration current. And the pure nitrogen or hydrogen gas is bubbled through the solutions. So you look at here, that is the inlet for nitrogen gas, isn't it? So in which the nitrogen gas or hydrogen gas is bubbled through the solutions to expel out of oxygen. Okay, we will discuss in the later. So then what is the purpose of using this nitrogen and what is the need to remove the oxygen? Okay. And suppose if you consider analyte solution containing a cadmium ions, and then the cadmium ion is discharged at the cathode, that is cadmium 2 plus 2 electron gives cadmium, that is the reduction, the gain of electron, the reduction is taking place. So then we are just gradually increasing the voltage which is applied to the polarographic cell, and the current is recorded. Now the graph is plotted between applied voltage and current. This graph is called polarogram. Okay, now this diffusion current is directly proportional to the concentration of the analyte, and it is used for the quantitative analysis. Okay, and this half-wave potential is a characteristic of every compound, and it is used for a qualitative analysis. So one can use this polarographic method for both qualitative and quantitative analysis. Okay, so in that instrumentation, from that principle itself, we study about the dropping mercury electrode, DME. Okay, so why we use why the dropping mercury electrode is used in a polarography? Okay, so we'll see. So in the working electrode, the mercury is continuously drops from the reservoir through the capillary tube into the cell. Okay, so then why we choose that DME is selected in a polarography? Because here the surface area is reproducible. That is, at each and every drop, the new surface area is created. Okay, and electrode can be renewed, and it thus eliminate the poisoning effect. Okay, and also this mercury forms amalgam with many metals. Okay, at that once the diffusion current starts, isn't it? At first, initially, the metal, once it reaches that surface of DME, first it forms amalgam. Then it get reduced at the surface. Okay, so here the mercury forms amalgam with many metals. So that we are using that mercury. And the surface area can be calculated from the weight of the drop. So it is easy to calculate the surface area. Okay, so even though it has a number of advantages, it has some disadvantages also. Okay, so then what are they? That is, here the capillary is very small. Sometimes it can be easily blocked by any of the impurities. So another thing is, here the mercury is very toxic. So we have to handle the mercury very carefully. And the surface area of each drop of mercury is never become a constant, and that is a very big challenge over that the polarographic method. And here this dropping mercury electrode cannot be used at a higher potential, that is plus 0.4 volt, greater than 0.4 voltage. So because at the higher potential the mercury get oxidized, so one can use that mercury to the lower potential only, that is less than 0.4 volt. Okay, so these were the some of the advantages and disadvantages of dropping mercury electrode. Okay, so we look at this polarogram. We already discussed about the polarogram. In sometimes in the polarogram we are getting the graph something different, isn't it? That is called the polarographic maxima. So here instead of getting a sigmoidal shape, so we are just getting a small hump in the polarograph. Okay, so what is this reason? So there is a maxima in the diffusion current. So that is an increase in the current above the limiting value in the form of maxima, which is oftenly noticed in the polarogram, that is called as polarographic maxima. And it leads to error in determining the half wave potential, because if it is a sigmoid, suppose the half wave is here. Okay, if suppose you are getting a polarographic maxima, then the half wave potential may change. Okay, it leads to some error in determining the half wave potential and diffusion current also. So then how to eliminate this polarographic maxima? Just by using a maximum of suppressors. Okay, which will increase the viscosity of the medium, that will eliminate the polarographic maxima. Okay, so here the suppressors are like just a surfactants, gelatin, dyes and surfactants like a triton is used. Mainly the gelatin and the surfactant is used to reduce the polarographic maxima. Okay, and that in the instrumentation we discussed the nitrogen or hydrogen gas is bubbled to expel the oxygen. Okay, so why we have to eliminate this oxygen? Because if suppose there any oxygen in that unknown solution, then we will get one separate curve for oxygen, that is called oxygen wave. So you look at this. So again, then an increase of current above the limiting value in the form of maxima is often noticed in the polarographic maxima, as we know. And here the oxygen present in the irreducible species in solution, it produces a double wave in the range of 0 to 1.0 volt, is due to the reduction reaction. Okay, it is due to the reduction reaction. So because this wave interfere with the analyte wave. Okay, that is you are getting, in addition to the analyte wave, you are getting one more wave, that is due to oxygen. Okay, so then why you are getting an oxygen wave? Because the oxygen get reduced to hydrogen peroxide. Further the hydrogen peroxide get reduced to water. So in addition to that reducible species, that oxygen is also getting reduced. So we will get one more diffusion current. Okay, so that the oxygen must be removed by bubbling the nitrogen through the solution for 5 minutes to expel the oxygen from the solution. Okay. Okay, so then what are the factors which affecting the diffusion current? So we discussed the two things. The one is the polarographic maxima, which will affect that determination of diffusion current, and another one is oxygen wave. In addition to that oxygen wave and polarographic maxima, we have some more factors which will affecting the diffusion current. Then what are they? The first one is concentration. So here that concentration, that is the diffusion current is directly proportional to the concentration, and the next one is temperature. So here the diffusion current is also varies with the temperature, that is directly proportional, because the temperature and viscosity of the medium affect the diffusion coefficient. Okay, so this so that diffusion current is also varied. The next one is capillary characteristics we discussed, that is the size of the capillary, drop time, and the pressure of the mercury will affect the diffusion current. Okay. The next one is advantages of polarography. So here that only the small volume of sample is required. So with the small volume one can measure the qualitative and quantitative analysis, and even the turbid and colored solutions can be analyzed, and it is used for the determination of the substance which are not electrochemically active. Okay, usually the electrochemically active substances are analyzed through the polarographic method. So now this electrochemically inactive or converted into electrochemically active, then it is used for the polarographic method, and it is a high speed analysis and it is a highly sensitive also. Okay, so then we will come into that. What are the applications of polarography? So from the starting itself we telling about the qualitative and the quantitative analysis. That is, it is used in the determination of concentration of drugs, metal ions in the given sample, and the half-wave potential gives the characteristics of the organic matters. And also one can determine the concentration of the inorganic compounds such as cations and anions in the presence of some interfering ions. And also one can determine some of the organic compounds, and one can estimate the dissolved oxygen with the help of oxygen wave, and another thing is pharmaceutical. So it is mainly used in the drugs can be analyzed by the polarography. Okay, so now up to this we have discussed about that introduction of the polarography and its definition, the principle, and the instrumentations. What are the different kinds of current appeared in a polarigram, and what are the applications and advantages of this polarographic method? These are all we have discussed. Okay, so I think definitely this video will help you for a better understanding of the polarography. Thank you.